Okay. Question number 6. We're going to look at the integral of cosine over the symmetric interval from negative pi to pi. Now, the cosine function, if we recall, is an even function. Cosine was even. Physically, what that means is the function is symmetric about the y-axis. This is your y-axis. Your function is symmetric about it. It's even. So for an even function again, let's remember, let's get this out here out of the way. Try to find what we need. It's going to be equal to twice the integral from 0 to pi cosine x dx. All right, so let's get what we're looking for. All right, well, if you go all the way back here to take a look, when we have even functions right in here over symmetric intervals. Okay. So we're going to have to get the area from 0 to pi. Notice it is a net area from 0 to pi. That integral that you see is this portion here. Remember, this is x is pi. Y-axis is x is 0, and this is x is minus pi. So we just have to find that area there. And the integral of cosine is sine. You evaluate this from 0 to pi. So this is our antiderivative. Let's change the color. We need f of pi minus f of 0. So 2 sine pi minus 2 sine of 0. Let's make sure we can see pi here. Sine pi we know is 0, and sine 0 is 0. So it looks like we get 2 times 0 minus 2 times 0. 0 minus 0. The answer here is just a 0. Now, I just want to point out to you that it looks like, yeah, the positive area above the x-axis is the same as the area below the x-axis. So that net area should be 0, and that's what they're saying. So this net area is 0, which means double that really is 0. And Math Chat GTP looks like it agrees here. If we take a look. Okay. Compare that example for the symmetric interval of negative pi over 2 to positive pi over 2. Recall that the sine function, is an odd function. So we know that this area will equal 0. There's no integration we need to perform, just the knowledge that we have an odd function over a symmetric interval. Now, when we look at the picture here, this is where x is negative pi over 2, this vertical line. X is positive pi over 2, that vertical line. And in blue here, we have the area above the x-axis. And in red, we have the area below the x-axis. Positive area here, negative area over here. And essentially, we just use the fact that if we integrate over a symmetric interval, any odd function, that area is 0. All right, we got to know about tangent now, because the interval is from negative pi over 4 to positive pi over 4. The tangent function, if we recall, is an odd function. So we know this area is 0. And we're done without having to do any integration. From our picture, we can see the symmetry of the curve for being odd is not just symmetric about the y-axis, it's also symmetric about the x-axis. We mean this is symmetric about the origin. And so the net area, I won't label this, the limit's down here. If you want, you can say, well, that is where pi over 4 is. Negative pi over 4 and positive pi over 4. So what you're looking at is the net area will be 0 here because of the symmetry of the curve over the symmetric interval. So for this situation, we notice number 8, the interval is symmetric. It's from negative 1 to positive 1. But we don't know if this function is even or odd. So I'm going to write up here, demonstrate to you again how we can figure out whether this function's even or odd. Maybe we'll just do it down here. Okay, so if this is my function, to say it's even or odd, we look at f of minus x, which is negative x over 1 plus minus x squared, which will be negative x over 1 plus x squared. And we get negative x over 1 plus x squared, which is negative f of x. So what this means here is that our function is, in fact, odd. This is an odd function. Okay. So because this is a symmetric interval over an odd function, the area equals 0. We don't even have to integrate. And you can see from the curve here that you have an equal amount of area above and below, because odd functions are symmetric about the origin, symmetric about both the x-axis and the y-axis. So, okay. Number 9. We have a symmetric interval from negative pi over 4 to positive pi over 4. Your function is x squared tangent x. So we have to figure out whether this function is even or odd. To do that, we have to evaluate f of minus x and see what it equals to. Just plug in a minus x wherever there's an x. This is x squared, and this will be minus tangent of x because tangent is an odd function. We get minus x squared tangent x, which means we get minus f of x. And sure enough, this is an odd function. That's essentially the proof. So because this is an odd function over a symmetric interval, we don't have to integrate. We know this area, or we know the answer is 0. Taking advantage of the function being odd over a symmetric interval. If we look at the curve here, you can see there's an equal amount of area above the x-axis as there is below the x-axis. So that net area is going to be 0. This is symmetric about the origin. Okay. We got to see what's going on with this function, x to the 4th sine x. We have a symmetric interval again. F of x is x to the 4th sine x. So evaluating the function, when the input is negative x, we get negative x to the 4th sine of negative x, which gives us x to the 4th minus sine x, because sine is odd. So we get negative x to the 4th sine x, which is negative f of x. Your function is odd. So you have an odd function over a symmetric interval. This integral equals 0. Odd function. Looking at the curve, you see you have an equal amount of area above the x-axis as you have below the x-axis, and that's only because the interval you have is symmetric. This is from -1 to +1. So as you can see, this is how we can very quickly evaluate integrals without, in most cases, well, at least in half the cases, only when it's a odd function over a symmetric interval, the area is going to be 0. And I believe that concludes, the demonstration here. So I'll send this to you guys. I hope you guys enjoyed the video.